Welcome back. This is lecture 27 in our series, and today we continue what we have been doing for the last two videos, which is instead of truncating our perturbative series at the very first order and then calculating cross sections from it, we have been trying to look further down that series. In fact, to look the whole series and try to make affirmations about objects which are sums of a lot of terms in our series, maybe resum the series somehow, or at the very least find recursion relations between terms in that series. Right? And today we continue on that trend. Right? Specifically, we'll deal with two subjects today, which are sort of related, but not exactly the same. One is the Dyson-Schwinger equations, and the second one is the word identities. So I put some references here, and let's start with the Dyson-Schwinger equation. The idea here is to try to find an equivalent to this classical equation, right? Which is our familiar result coming from the extreme action. Right? We know that in the presence of sources, this is valid. And we want to find some quantum equivalent of that. We already found that for the vacuum expectation value of the field, I can exchange this action for the effective action, and then this is true. But that's specific to the vacuum expectation value of the field. Now I would like to know if there's some equivalent equation to this for, I don't know, a general state, not just the vacuum, right? And to get to that, let's consider a very simple identity, right, of integrals. Right? We know that this is true. If, right, and only if, this function goes to 0 at plus and minus infinity, right? Then that integral is 0. I want to start with the similar thing for path integrals, right? In fact, in Euclidean space, it's even easier to find something like that because I don't need that condition, right? If I write a path integral over phi of the functional derivative of phi exponential minus the action phi plus j phi, right? This is the function I have here, it's not this functional, right? Is 0. That is true in Euclidean space because even the boundary terms don't need to be 0 because I have cyclic periodic conditions for my path integral, right? And then I can use this equation, right, to rewrite this in the following form. I can write my path integral, right? Let me do this derivative, right? I'll have the exponential again, which I'll just copy here. And I have the derivative acting on the exponent here, which will be del s del phi x plus j of x, right, times this exponential. And since this is the same as above, this needs to be 0. In which I already got an interesting thing, because if you pay attention to what I am calculating here, this is the expectation value of s phi x, del s del phi of x, plus j of x, right? And I'm saying this is 0, right? In any state, I mean, I'll choose the state by choosing the details of the path integration here. For instance, I could take this period to infinity and go back to the vacuum. But this is true more generally, right? This is actually an interesting thing because now I have already a quantum equivalent of something that was valid classically, and that gives me a limit that I can go back to the classical one and get the same equation, right? You have seen this in other places. Just think of Ehrenfest theorem, for instance, where you have equation which is very similar to a classical one, but valid for expectation values instead of just these functions, right? These classical functions. Right? And that's what we get here already for this particular equation. Now I want to take this further. Right? First, let's use a trick that is a very useful one when we are doing path integration. Right? This is a derivative of the action, functional derivative. So this will be again a functional or a function in phi's, right? A function in this case of many phi's. And I can rewrite this object by substituting the phi's by derivatives in j, because this is multiplying this exponential, so I can replace whatever polynomial of the fields that show up here for a polynomial of derivatives in j. And when I do that, I can take this whole bracket outside the integral. So let me do that. Right? I just write this. Del S del phi x, where I substitute every phi in that expression by a derivative in j of x, right? Plus j of x, acting now on the path integral of this exponential. And this is still 0 because I didn't do anything, right? When I go back with this thing inside, these derivatives act on j, take a lot of powers of phi back, and you reconstruct that equation. If that is true, this one is true. And now, if I think that I'm considering the boundary conditions here, so that this is the partition function, then I got to this equation, right? This will be just z of j equal to 0. Let me put a box around this, because this is the equation that we wanted, right? The Schwinger-Dyson equation, or the Dyson-Schwinger equation. You see it both ways around different books. Right? And this is almost trivial, the way we did it here, right? It's almost just a mathematical identity. But this is not the way it was derived for the first time, right? The way this was obtained on the first time was not just as one equation, but instead of many different Schwinger-Dyson equations, that's why you usually see these in plural, which were relations between diagrams, which were not trivial at all. Right? But that's all contained in here. This is the most compact and easy to derive version of the Schwinger-Dyson equation. Right? But we are doing it the opposite way of the historical order. We first got here, and now we're going to extract many equations between these relations between diagrams, starting from this, which is the compact form. In order to do that, let's write the action for my scalar theory in this way. Let's get a kinetic term and some interaction term that for now I'll write it like that. So the only assumption I'm making so far is that the only Gaussian term is this, so the mass for this field is 0, right? At least at the Lagrangian level. So let me differentiate that in relation to phi. Take the functional derivative of this. Let's choose point x, and then this side of the equation becomes delta minus 1 of phi, which is a function of x, plus also the functional derivative of the interaction in relation to phi of x. Now, if I apply delta, right, the inverse of this operator to both sides of this equation, then I get, and then I integrate, right? I basically just apply this to both sides of this equation. d for x delta y, say y minus x, and I apply this to both sides of that equation, right? This side just becomes delta scalar this thing, right? Now the x is integrated over, so this is a function of y. In here I get phi of y, because this delta will get the delta minus 1 here, then that becomes just the Dirac delta, and I do the integral. And in here I have the same, is delta scalar del interaction, the interaction part of the action, del phi, which is again a function of y. Now I want to go back to that equation, right? That one. But in order to do that, I also apply this to both sides of this equation. So I can just substitute this here, right? And I get delta j here, right? So let me write that. There's a minus sign there. So what I get is minus delta scalar del s del phi of y, right? With the provision that I'll substitute phi's by del j's in this part of the expression, plus delta j of y, right? This is a function of y, acting on z of j should be 0. Huh? So now I'll just replace this expression here. This will be, so this right hand side, I need to replace phi by del j. So the first, and don't forget this minus sign, so there will be minus del j y, right? This first part. The second one is minus this thing under this exchange, goes here, plus this part, right? So these two are just coming from here, and now delta j of y acting on z of j is 0. Let me reorganize this and also replace y, this variable y, for x, just to keep it in line with my notes. So this part acting on j, I'll go to the other side of the equality. This will be just del z del j of x equal, and then all these things, right? Let me put this one first. Delta j of x multiplied by z of j minus this thing, which is delta scalar del si del phi. All of this is a function of x, and I have to replace phi by derivatives in the source, acting on z of j, which is a fairly important equation. Let me put a box around that. Right? This is sometimes called the Schwinger-Dyson equation for z, right? For the partition function or the generating function. Right? And it is very convenient to extract the relation between diagrams I'm seeking. Right? In order to do that, now I have to specify the interaction. Let's take a simple interaction that is simple enough to quickly show what I want to show, but not so simple that becomes trivial. Right? The one I'll choose is this one. Which is a combination of a phi 3 interaction and a phi-4 interaction. Let's suppose we have both in our Lagrangian. In this case, I can go back here, right, and write that del z del j of x is, this is the same, does not depend on the interaction, but now this part I want to write more explicitly, right? So there's an integral in here, let me call that y, right, d for y. There's a propagator, this is a function of x, so there's a propagator from x to this point where I have the integral, x to y, right? And this guy on the right side here is like a del interaction part, del phi, which is a function of y, right? This is integrated over, right? The way to obtain this from this guy is to make a del phi y acting on the integral of the, this is the action, right? So this is the integral of the Lagrangian, a d for z of the interacting Lagrangian, right? So I need to make this derivative in phi, goes in there and acts on these phi's here. In any case, I'll always get a delta 4 of z minus y, right? So I want to write that. This is a d for z. This derivative goes in here, gives me a delta 4 of z minus y. And now I have to write these guys with one less power because that derivative took one of these powers out. Also, the factorial here is one less, right? But remember, all of these guys, I have to replace whatever is left after I calculate this guy. I have to replace phi's by del j's, right? So I have to write this in terms of derivatives in j. So what goes in here is like lambda 3 over 2 factorial, because a power 3 came down as I did this derivative. Right? I have phi squared, but I need to replace by del j's. So it's a del 2 del j z del j z. Right? That's this term. Right, after this derivative, plus lambda 4 over 3 factorial, right, because the power of 4 came down. So I have a delta 3, right, now 3 powers only, del j z del j z del j z. And this is all acting on z of j. So I got a z of j on this side. I can use this Dirac delta to do one of these two integrals, doesn't matter which, right? And then I get the expression that I have down here, right? Now, what do I want to do with that? I want to turn this into a relation between green functions, right? In order to do that, let's take this expression. First, let's call x by the name of x1 and do n minus 1 extra derivatives everywhere on both sides of the equation on variables on j of x2 to delta j of xn. So that on the left hand side here in the end I'll have n derivatives going from the derivative in j of x1 to the derivative in j of xn, right? And on the right side we'll see, right? On the left side this becomes an object that is well known to us, right? That will be del n z of j del j x1 to del j of xn, right? If we in the end take j to 0, this is the green function in the absence of sources for n points, right? That's what I'll get on the left-hand side if I do these three operations, call x, x1, do extra n minus 1 derivatives, so I have a total of n derivatives, and of course, also I need to take j equal to 0 at the end, right? Forgot to mention. Okay. Now what happens with the other parts? Let's look at this one first, right? When I do n minus 1 derivatives here, right, I'll get del n minus 1 derivatives of, let me put it here, del j x2 going all the way to del j of xn, right? It does not start from x1, right? And this is acting on delta j of x, z of j. So these derivatives have to act here, right? And they can act on this j, or in the j's there are on the exponentials here, right? I know what happens when they act here, right? They just become a green function again, right? Some certain number of derivatives acting on z will be just the green function, right? But there's always one of them that will have acted on this guy, right? So let's take the combination where j of x2 has acted here, right? And the rest just go and acts on z, right? In this case, when this derivative acts here, right? Instead of this j, you get a delta of, there's a hidden integral here, right? So that variable will become x2. So the propagator here, right? Remember this now I called x1, right? So the x that was here is x1. So I'll get a propagator from x1 to x2. And then all the other derivatives are acting on j. That will be a g n minus 2, because I already had n minus 1, and I use one of the derivatives here, right? Of x3 all the way to xn, right? But that's not the only option, right? I have a product rule there, right? So I also have the option where the derivative in j of x3 acts in this j, and all the other derivatives act on j, on z, sorry, on z. So I also have a term with x1 minus x3 and a g n minus 2 of x2, x4, all the way to xn. So this one does not depend on x3. In all the other variables, minus x3. And that goes on, right? This, I have many terms like that, which are a propagator from x1 to some point, right? And then a green function, which is a function of all the points minus x1 and whatever other point that appears here, right? It's always x1 and some other point, and you go through all the combinations, including xn. So if I go back to my equation here, right, doing these two, I still have to see what happens to this part, but the first two are clear, right? And what I'm getting is that gn x1 xn is equal to this part, right? So that's left hand side, the right-hand side, the first part is this. Let me copy it. Let me write this in general terms. So the last term will be x1 minus xn g n minus 2. That depends on x2 all the way to x n minus 1. Right? This is the first and the last term of this part, right? And then for the last part, right? This part. The extra derivatives will go through this, right? Because there's no j's here. And we'll get together with these extra j's here, right? So now I have n minus 1 derivatives acting on z, plus 2 in this case, and plus 3 in this case, right? So what I get is green functions of more points now, right? I get a minus integral in d for z. That's the part I'm just copying. Z1 minus x1 minus z, because I baptize x as x1 now, right? And this is lambda 3 over 2 factorial. And I have a green function, which is of n plus 1 points. Which points? Is twice a function of z, because I had 2 derivatives in z here, right? In j of z, right? And then a function of all these guys. So that's x2 xn. Right? And the same thing for the other part, right? I have lambda 4 over 3 factorial g n plus 2, because then there even one more derivative in j of z x2 xn, all right? And there you go, all right? That's the relation I wanted to show. So notice that what appeared here first is a relation between green functions with a different number of external points, right? Green functions of different number of variables, right? n minus 2, n plus 1, n plus 2 here, right? And the second thing is that I didn't do perturbation theory here yet, right? I'm taking these expressions should be valid at all orders in perturbation theory, because I'm using the full green functions here, which is important. Now let's try to express these in terms of diagrams. On the left hand side, what I have is a green function that connects to xn points. I'll keep x1 separated for the rest, because you see x1 has a special role on this right hand side, right? So this x1 goes to a complicated green function that actually includes all the diagrams. Now remember my convention here, right? Box means all diagrams. If I put a j inside, means in the presence of sources, but in the absence of sources, I just take this j out, right? Because this expression is for j equals 0. In fact, for instance, here, right, I forgot to write, j equals 0 means I don't have, for instance, the term where I have delta j with all the derivatives acting on z here. I didn't include that here because I'm taking j equals 0 at the end. The same reason the z is in these green functions in the absence of sources, right? And this is connected to xn points, so x2, x3, etc., right? All the way to xn, right? Let me put like that, just so I can do my little diagrammatic thing. Now, this is equal. Now let's try to write the right-hand side. Let me copy this because it's useful. See, in here I have a green function that is a function of all points with the exception of these first two, which are in fact connected to each other. I have a propagator from here to there, right? But and I have a leftover green function which depends on two less points now. The next term, which is not written here, would be something like that, right? Something where I connect x1 to x3. This goes behind, is not crossing that line, right? Connects x1 to x3, right? The term was written up there, right? And a green function that depends on everyone but x1 and x3. And this goes on until the very last term on this line, right? Which is the one that connects x1 to xn, right? And then depends on all points from x2 to xn minus 1. Right? So this is what this first line is doing. Right? But I also have these contributions, which now have extra points. So I have a minus 1 over 2 factorial. I have a point that goes from x1 to z. Right? So there's a propagator from x1 to this point z, which is it's not a real point, right? It's integrated over, so I could suppress, but I'll leave it there just because it helps us see, right? And there's two lines going from this green function into z. That's why it's kind of odd to say a function depends on z twice. But what this notation really means is that I differentiated these twice, so whatever complicated diagram is here, it's connecting to z through two lines, right? There's a complicated diagram here, but two of its lines go to the same point, this point z, right? And then I can put the box here to represent this set of, this sum of very complicated diagrams that also depend on all the other points. So x2, x3, all the way to xn minus 1 and xn. And the next one is very similar thing, right? There's a minus 1 over 3 factorial, right? There's a propagator from x1 to z. And then there are three, whatever complicated diagrams will be in the box here, right? There are three lines going from that diagram into the same point here, right? Z on the left, right? And then, of course, this box also connects to all these these n minus 1 points, right? xn minus 1, xn, right? These two factorials here, you could think they are symmetry factors associated with these lines, but that's not really guaranteed, right? I have to keep this factorial because, say, for instance, this line could be something very simple, like something doing this, x2 connecting to point 2, 3, and the other one going to point n minus 1 and n, right? And then there's no real symmetry factor. You have to be careful with symmetry factors here. So for now, I'll just keep this 1 over 2 factorial, and you have to see when you draw the diagrams if there are other symmetry factors that come from here. So you see how these Schwinger-Dyson equations are leading to relations between green functions at all orders in perturbation theory and green functions with a different number of external points, you see here, right? It's multiplied by the propagator, of course. Everyone is a function from x1 to xn, but you see the green function here is not the same as there, right? In fact, you can actually use these kind of Schwinger-Dyson equations to recover the perturbative expansion, right? To see that, let's specialize this one up here for the 2-point function. So let's take g2 of x1, x2, right? And let's specialize that one up here, right? If I take n equals 2, these terms, I'll have just propagators, and g0, the function of 0 external points. And there's only one term like that between x1 and x2. That's delta of x1 minus x2 times g0. Remember, g0 is the sum, is just this box, right? It's the box without any external lines, is the sum over all the vacuum bubbles, right? This term now becomes just minus d4z delta x1 minus z, right? And then this with n equals 2, right? So lambda 3 over 2 factorial g3 of z x2. Remember what these two z's mean, right? Means just that I have complicated diagrams, but both lines will go to z, right? And then the other part is just lambda 4 over 3 factorial g4 of z x2, right? Diagrammatically, right, this is just this relation x1 x2, right, on the left here, is equal to x1 going to x2 times all the vacuum bubbles. I remember we're talking about the full green functions here, so I still have bubbles, right? Minus 1 over 2 factorial propagator from x1 to z, 2 lines going into the box, and then an extra line going to x2, and minus 1 over 3 factorial, right? A line going from x1 to z, 3 lines going into the box, and a line, a 4th line, because this is g4, going into x2, right? Now I can look at this expression, right, and use the Dyson-Schwinger equation to write G3 and G4. See, I can use the same equation for G3 and G4. For instance, for G3 of Z x2, right? Now, the same way, you see, in this equation, I chose x1 to be that spectral point, right? That appears everywhere in the propagators, right? But I could have chosen x2. This is symmetric, right? I could write the same Dyson-Schwinger equation for x2. I just have to go back when I was proving this equation and call this x2 and do the same for everything else. So I could take any point to be that special one that I'm keeping to the left here. In fact, that shows there's nothing special about it. But this equation is written in terms of some point that I choose to be the one that is in every propagator, right? So when I want to use that for G3 here, I have to do the same. I have to choose one of these points to be the point I'll write the equation for. And I'll choose this one, right? So in this case, I'll have a delta Z minus Z, G1 of x2, plus a delta of Z minus x2, G1 of Z, right? So that's the trick. I keep Z here. And once I contracted with Z, and then G1 is of x2. And the other instance, I contracted with x2, and then the 1-point function is of Z, right? And then I have this piece, right, which is minus lambda 3 over 2 factorial. Call this, now I don't want to use Z because I'm using Z as an external point for this guy, right? So I'll call this a D4W, right? I have a delta of Z minus W, and the green function 4 points, right? Remember, on this part, I increase the green function by 1. In this part, I increase the green function by 2. And the integration variable that shows up here appears twice here and thrice here, right? So that's what's happening here too. So this will be a 4-point function of W. This one Z is actually already here. So I have just Z x2. Right? And the next term will be lambda 4 over 3 factorial, right? D4W, delta Z minus W again, because that's the same, right? And then I get a G5 of W, ZX2, right? You see? So I'm using that equation to plug here, right? This G3 is where I'll put that. So diagrammatically, what I'm doing is taking this diagram here, right? Separating that box with 2 lines coming out. So that's G3 of ZX2. It's just the diagram to the right of this dashed line, right? And this guy I'm writing now as x2 z, right? This is just this piece, right? I'm using Schwinger-Dyson equations here, so I'm getting z, right? This is this part times a box that depends only on x2, right? Plus this guy, but now it depends only on z, and there's a propagator from z to x2, right? Minus 1 over 2 factorial. Let me copy this, right? And here I did this, right? There's a, I won't write w, so there's a propagator from z to this point, which is w. I'm not writing it explicitly. And it branches, so now I have a 4-point function. 2 of them connected to w, 1 connected to z, and 1 connected to x2, right? And the last piece here is just minus 1 over 3 factorial. Same thing, but with a third line, right? So now there are 3 lines going to w here, and this box ends up having 5 external lines, so it is a G5. If I do the same for G4, then I obtain this expression, right? And you see here I choose Z1 to write this expression in terms of this first Z, to write this expression in terms of, right? So there's these deltas that connect to Z. This factor 2 is because there's 2 options where I could just connect directly. And then you have the propagators. Instead of G4, I have G2 here, right? Because I'm removing 2 legs. Yeah? And of course, in these terms, then I increase the size of the green functions, right? So I had G4 here. I write it in terms of G5 and G6. Yeah? Now I can go back with this expression for G4 and this one for G3 and plug them here. Right? I'll take this expression for G2 and I'll substitute this guy and this one by these expressions I have just shown. And this is what I get, right? It may seem, just looking at this expression, that I'm complicating more and more because I'm getting green functions. Now it's a 5. Here you see a 6-point green functions, which are more and more complicated. And if I keep doing that, right, I can write the 5 in terms of the 6 and the 7. I can write this 6 in terms of the 7-point or the 8-point green functions, right? Maybe I'm just increasing the complexity here. But take a look at these coupling constants, right? At the same time I'm increasing the complexity of the green functions, I'm also increasing the powers of these couplings, right? So this term is linear on lambda 3, but this one is already proportional to lambda 3 squared, because there's lambda 3 out here and another one in here. This term is proportional to lambda 3 times lambda 4, so 2 powers of the coupling constant. So when I do that, at the same time I'm increasing complexity, I'm also increasing the powers of the coupling. That means that if these couplings are weak, right, if this is a small parameter, I can truncate that. I can at some point say I just want to know this quantity up to some powers of lambda 3 and lambda 4, and then I can truncate it and I'm recovering the perturbative expansion. Just to give you an example, suppose I just want to know this 2-point function. Let me remove myself from the way here. Suppose I just want to know this 2-point green function at, say, order lambda 3 to the 0, so the terms that are independent of lambda 3 and linear in lambda 4. Let's suppose I'm interested in that part of the 2-point function, right? So this first term stays, right, because this is the free theory contribution, but everything that is in red here goes away because this is all proportional to lambda 3 and I don't want any power of lambda 3, right? So I can ignore everything that's in red here. Now this second term, right, it's linear on lambda 4 already at the very least, right? So this piece and this piece I can ignore too, because this will be proportional to lambda 4 times lambda 3, right, which I don't want, and this one will be proportional to lambda 4 squared. So I really only have to look at these two guys here, this one and this one, right? And now I also know that this guy, right, this G2 of ZX2, and I can use a similar thing for the second one here, right, is just delta of Z minus X2. Again, I'm using the Dyson-Schwinger equation, right, G0 plus, right, this is that first part that is always there, right, just connect these 2 points and write the green function. And then there's the part that depends on lambda 3 and lambda 4, that will be linear, at very least linear in lambda 3 and lambda 4. But since this guy right here is already multiplied by lambda 4, I can ignore this piece because it will be a higher order correction to my calculation. So, and that means, now going back to the original expression, that my G2 will be this part, right, plus now this integral right here. So let me just rewrite it, won't be easy to copy. Lambda 4 over 3 factorial, integral of d for z, delta x1 minus z. And then I have this part that I'll use this expression, so it's a 2 delta z minus z, right? This is just this. Now delta z minus x2 times g0. This is all I have here. Plus, now this part, right, is just delta z minus x2, and for g2 here I use this expression again, is delta z minus z, right? Instead of zx2 I have dz, g0, and this is all up to order 1 in lambda 4 and order 0 in lambda 3. So there are more terms which are at very least linear in lambda 3 and quadratic in lambda 4. I'm ignoring those extra terms, right? You see there's an overall G0 here, which is the vacuum bubbles, right? I can factor this guy out. You see it's appearing everywhere, right? I can factor this guy out in front. So if I only interested in the connected diagrams, the thing I want to calculate is really this, right? Because that's what shows up in observable, right? You have to normalize the green functions by the vacuum bubbles. And then I can write this thing more explicitly as delta x1 minus x2. You see this guy and these are the same, so there's a factor 3 here that goes and cancels out the other one. I end up with minus lambda 4 over 2 integral of d for z delta x1 minus z delta z minus z delta z minus x2 plus, of course, higher order corrections. Which is in terms of diagrams a result that is known to us, right? This is just a propagator from x1 to x2, right? Plus a term that is propagator from x1 to x2 passing by a point C in the middle where you have this small loop here, right? And you see even the symmetry factor, which is a factor 2, right? In this case, remember that 3 factorial could not be a symmetry factor from the start, right? I warned that unless you really expand these grain functions, you cannot interpret that as a symmetry factor, because different pieces that are hidden inside those boxes will have different symmetry factors. But once you do the expansion, you can find the symmetry factors, right? And you see you're recovering the usual expansion for lambda phi 4, which is the one we choose. We choose to take the free theory in regards to lambda phi 3, right? And that shows us how much information is inside the Schwinger-Dyson equations, right? You have the information about the whole perturbative series. I could go on and get I could get the whole perturbative series from this equation. But that's not the easiest way to get the perturbative expansion, so that's not why people use the Schwinger-Dyson equations. The point is that these relations between different green functions are valid to all orders in perturbation theory, and sometimes you can use that to get non-perturbative information about theories. This is used in QCD a lot. The next subject I want to discuss is what we call a word identity, right? The word identities in general, right? And the idea comes from theories with symmetries, right? So imagine, just to start, some transformation of the field, right? Which is a continuous transformation and can be written in the following form, right? So epsilon is some small parameter, right? These are the generators of the transformation, right? And this is the starting field. So I can actually rotate fields. You can imagine a field with many components. These matrices will mix those components amongst themselves, and then you transform from phi to phi prime, right? And this is, I'll call this a delta phi, right? And this index is contracted. This is index A is contracted. So this is just delta phi I, right? This index is depends on the group, right? If this is a group of transformations, I don't know, SU2, for instance, has 3 generators. And so A goes from 1 to 3. Now, if I assume that this transformation is a symmetry, that means that my action will not vary, right? So this is the variation under this transformation, right? This will be 0. Right? We know that I can write this transformation as the transformation of the Lagrangian, right? Del phi I, del phi I, right? Plus how the derivatives of the field change. Right? Del mu phi I, del mu delta phi I, right? And I'm assuming these two things commute. So the variation under this transformation passes through the derivative, right? And now I can do a trick here to rewrite this this expression the following way. I'll just sum and subtract a term. So del L del phi I is just what we have here, right? And I can do a integration by parts, throw this derivative out here. That will give me a del mu del L del mu phi I This is all multiplying this delta phi I here, delta phi I, and this is the surface term, del L, del mu phi I, delta phi I. Now, if this is a classical theory, right, or in other words, if this field satisfies the equations of motion for a classical theory, then this part is zero, right? This is just what you get from the Euler-Lagrange. This is the Euler-Lagrange equation, right? So that part is zero. And that means that the variation, look at just this part, the variation of the Lagrangian classically, right? And by that I mean, if I use the classical solutions for the field here, right, is equal, and now I'll substitute delta phi I by this expression up here, right? So this is I epsilon A del mu del L del mu phi I T A I J phi J, right? This case, I just used this definition for delta phi I right here, right? And now this is zero, right? Because the first part is zero, the second part must be zero too, because I'm saying this is a symmetry. So the action is invariant over this, right? And what I'm saying is that I can name this guy just J mu A, right? There's an index A which is not contracted here, and there's mu. The I and the J's are all contracted, right? Which is another current, right? This is basically the Nether's theorem that I have just shown, right? And what I'm saying here is that classically, right, another word that you hear is on shell. On shell meaning these phi's are satisfying classical equations of motion in this context, right? This is a valid equation, right? But we know that our path integral, right? Suppose I'm talking now about a quantum field theory, right? Phi will be inside of path integral. Let's think about the path integral formalism. It's easy to see my point, right? Phi will be within a path integral, so it will be integrated over configurations which satisfy the classical field, the classical equations of motion, but also by off-shell configurations, right? Configurations that do not satisfy the classical equations of motion, right? If I say that that transformation is still a symmetry, I'm still saying that the variation of the Lagrangian, here I'm abusing a little bit, right? Instead of talking about the variation of the action, I'm talking about the variation of the Lagrangian, so I'm discarding a possible full derivative term, right? As some surface term, right? So I'm assuming the variation of the Lagrangian is zero. It is general enough to show what we want to show, right? Will still be zero if I keep this as a symmetry of the Lagrangian, right? This will still be zero. And that means that, let me rewrite this expression, right? This whole thing, now it's I epsilon T A ij times that thing under in the brackets. So I can copy all this here. I just have to replace this by a phi j, right? Because already I'm exchanging delta, right? In here I had delta phi I, but most of delta phi I is out here already, right? This is an epsilon a, by the way. So I epsilon a t a I j, right? And here I have phi j. And if this is a symmetry of my Lagrangian, this is still 0. So now, since the equations of motion themselves are not valid for off-shell configurations, right? So this is on shell. Now I'm considering the off-shell case. In this case, this is not 0, right? And that means the whole thing must be 0, and I lose my conservation equation, right? If this part was 0 independently from this one, then I would have del mu j mu equals 0 from here, but I don't, right? So in this case, I don't have the conserved current, right? Or there's no conservation coming from my equation. Now let me do a little trick, right? Suppose I go back to my transformation and I consider the same Lagrangian, right? But under a different transformation that now I make local, right? Other than that, it's still the same group, but I'm making epsilon a function of x. Don't be confused here. I'm not saying that my theory, my Lagrangian, is now invariant under a local symmetry. It's still the same Lagrangian. It's still invariant under the global symmetry only. I'm using this as a trick, right? So I'm changing the transformation, but my Lagrangian is the same. That means that in general it will not be invariant under this new transformation I'm making, right? In fact, if I want to write the full transformation of the action under this now, it will be d for x, I epsilon a of x, t a I j, multiplying this. Well, this does not change. Let me just fit it on screen. Right? This does not change. The only change is when I wrote this in terms of epsilon. Now there's a product rule, right? Because epsilon does not go through the derivative, right? So I get an extra term, which is the derivative acting on epsilon. So now I have a new piece, because epsilon depends on x, right? A new piece, which is this one, d for x, I del mu epsilon a of x, right? So that's what you get from now the derivative acting on epsilon. The rest is very similar, t a I j times del L del mu phi I phi j. Right? And this is the variation of the action now. Since I didn't do anything, I didn't change my Lagrangian, this is still true, right? So this part is still 0, because that's a conclusion that I derived from demanding the global symmetry, right? This Lagrangian is symmetric under the global transformation, right? Now, under the local, the action changes by this much. This other part is 0. Well, so my conclusion is that now I could write the variation of my action under a local transformation, which is not a symmetry, as this piece here, times the thing I call another current, right? This is again the same object I had here. I just need the TA, bring the TA inside, which I can do, right? In fact, let me do that. If I include the TA here, then I get J A mu of x. So the point of this trick was actually getting this equation. I was able to write the variation of my action in terms of the nether current, right? Of course, this expression is only obtainable to this transformation, right? Otherwise, the variation of the action is 0. Right? And let me also rewrite these in a very particular way, which will be useful for us, right? Which is that I'll just put the derivative here, epsilon x a del mu j mu a of x. This will be useful in a second. You see, the whole point is that I needed this expression. I need to write the variation of a Lagrangian under that transformation in terms of the nether current, right? This last step, of course, is only valid. There's a surface term, right? And I'm assuming epsilon is quite arbitrary. It's the parameter of transformation I'm using. I'm assuming it goes to 0 at infinity, so I don't have to worry about surface terms, and I can show this. Now, what I want to use this for, so these are preliminaries, right? We have seen Nether's theorem, which is valid classically, right? We have seen what happens if you include now configurations of the field that are not on shell, do not satisfy the equations of motion. That means that now the Lagrangian, this whole thing needs to be 0 and you don't have a conserved current, right? And I have shown that if you do on the same theory, you do local transformations, then this is how the action changes, right? So far so good. Now, what we want to do, and this is why I'm talking about this in the same video I talked about Schwinger-Dyson, is to do something similar to what we did for Schwinger-Dyson, right? We had equations of motion for the classical theory, and we want to write equations that look the same, but now in terms of expectation values, right? Which you expect to be able to do because of Ehrenfest theorem, right? So now we know that for theories like that, right, under that have global symmetries, you have some conserved current that looks like that, right? Classically, this is true. And I want to find, right, you expect to be able to write, at least in most cases, to write something like that, right? Which is true when I have operators inside this current, but for their expectation values, right? You expect, in fact, that in the limit where the quantum effects are not visible, right? If you go to the coherence limit, that you would go back here. So that's the idea, right? So let's try now, and we'll use especially this result, in order to get to something like that. Consider them the following path integral, right? Del phi of the exponential of minus s of phi, right? I can always write this thing again with a different name for the variables, right? This is just changing the name of the variable on a path integral. But now, if phi prime is obtained from phi by a transformation like that, an infinitesimal transformation, and the Jacobian from phi to phi prime is so that d phi prime is the same as d phi, right? The integration measure here, right? Then I can bring this to the other side, right? And write, I just remove the prime from here, right? And write that this minus the exponential of minus s of phi prime, right, is 0. And notice that's the second time we see something like that. Remember the discussion when we were doing the quantization of gauge fields, right? Keep that in mind. I'll go right back to that. Let me just get to the end. So this is obviously the variation of this exponential under this transformation, right? This is how the exponential of minus s of phi varies when I do this transformation, right? This subtraction. Of course, I should have the opposite sign, but fine, right? And this I can write, of course, as minus del phi, the phi, delta action of phi times the exponential. I'm just propagating the change here. So what I'm saying is that as long as these Jacobians cooperate, I'm showing that the expectation value of the variation of the action is 0, which is already in the form that I wanted, right? It's a quantum version of a classical result. But keep in mind, if these Jacobians do not behave, and we call these anomalous theories, right? In anomalous theories, these will not be true. I will not be able to prove that, even if that one is true, classically, right? So keep that in mind. We won't talk about anomalies now. This is for quantum field theory 2, usually, right? So that's what we wanted. Now, assume that this transformation I'm talking about here is the one that I used here locally. Let's suppose this is the transformation I'm thinking about. I'm not assuming that the action is invariant under that, right? Again, I will only assume the classical conservation of the global symmetry, right? But let's assume that's the transformation I'm applying here. Then I can rewrite this equation, right? I have the variation of the action here, and I have shown up here, right, that I can write under that local transformation the variation of the action in terms of this or this, right? I want to use that one. In that case, I can show that del phi of minus I d for x epsilon a x del mu j mu a of x times this exponential s of y is equal to 0, right? I'm just replacing the variation of the action by this thing that I have proven before, right? I can separate this integral in two pieces, right? This does not depend on the field, so I can write it out here. I have epsilon a x times the path integral. And this equation should be valid for any epsilon, right? Epsilon could have very different forms. The only assumption I made to get here is that epsilon goes to 0 at infinity, but in general it can be any complicated function. So that part will not be 0 in general, and that means that this one needs to be, right? So this is true, which is the word identity I was looking for. And of course, what is written there is just that del mu j mu a is equal to 0. So I got exactly the equation I said I wanted, right? Is the continuity equation for the current, but now the current is an operator, so I have this continuity equation for the expectation value of that operator, right? Which is nice, right? I can have more general expressions for that, right? Because sometimes these continuity equation will be multiplied by other things, and that should be true too in the quantum theory. Let me show what I am talking about. Suppose I take that same transformation and I consider the variation under a generic operator, which is a function of the fields of the theory. Then the variation of that operator will also be given by this. d4x by I del epsilon a of x times epsilon a of x, which is true for any small variation, right, of epsilon, right? And using the same logic as above, we get just write the integral twice with just changing the name of the variable and then subtract one from the other and assume there is no anomalies. You get that this integral here should be 0, right? The integral is exponential minus s phi operator of phi I, right? Same thing I did before, just wrote the same integral twice and subtracted it from itself, which is automatically 0. The only trick here is that I was able to assume there's no anomalies and assume the Jacobian was 1, right? Now, this I can rewrite in terms of epsilon using this expression here. Maybe it's just I d4x epsilon a of x times the integral del phi exponential of s phi, right? And then I have the variation of these two pieces, right? The variation of the exponential I already know is this del mu j mu a of x times the operator, and the variation of the operator is just minus I del operator del epsilon a of x, which comes from this part right here, and I had to fabricate an I here that was not present in the case of the operator. And that is again the same story, right? This needs to be 0. This part is arbitrary, so this part needs to be 0, which gives me a generalized word identity, right? This is just saying that this variation, this integral of the exponential of s phi, down here to get more space, del mu j mu a x times the operator phi I, it's equal to I integral del phi exponential s phi del operator of phi I del epsilon a of x. Right? So tells me how a product of current times operator varies, and this is very general word identity because it relates basically. You can use this operator as anything, right? And it's also useful for us because we can take this operator as the exponential of the sources. Let's see what happens if I do that. In this case, that same operation will lead to this equation, right? Again, the same trick, just getting an integral and subtracting it from itself, and then assuming the Jacobian does not change, right? I'll get the variation of the exponential of the action. And that operator, which now is just the exponential of the source term, which I can include here, right? And again, same thing I did with the operator above. I can rewrite this as d for x, the small epsilon of the change, right, times the path integral of the variation of this function in terms of epsilon. S phi plus phi j, right? Again, I could use that the variation in terms of epsilon of the action will give me this conserved current, right? Not conserved current, I mean this nether current, right? But I don't want to do that. Let me keep the variation in terms of epsilon, right? Because then, of course, this is arbitrary. So what needs to be 0 is this guy. Let me put a 0 on the left here, because I can work a little bit more on it, right? I know that, take this first piece, right? I know that the variation of the action in relation to epsilon a, right, can be written as the variation of the epsilon in relation to the field times the variation of the field in relation to epsilon a, which I know, right? I'm assuming that same transformation. So this will be just I t a I j delta s delta phi I times phi j, right? If I take delta phi and differentiate in relation to epsilon, I get this generator and the field at j, right? So I can use this here, right, and rewrite I t I j a, the path integral, times minus del s del phi I times phi j, plus the same thing for this guy, right? Which is easy. J does not depend on phi, right? So it's just j times delta phi, and delta phi is I, Tij, etc., right? So I just get Ji phi j. The same thing. The rest of the variation is out here. Right? And of course, I still have the exponential that I will just write very shortly here. Now this equation is equal to 0, and I can rewrite it in a very convenient form, right? Again, I can use the trick I always use, which is substitute the field here, here, and here by derivatives acting on j. Right? Whatever form I get differentiating the action in relation to this field will be also a polynomial in the fields, and I can just substitute that for derivatives in J. So if I do that, I can remove this whole bracket outside the integral and then get just the partition function, right? So what I'm getting at is that IFT-IJA times this bracket, which now I'll write like this, phi I x with phi substituted by del j, right? Plus ji, which is this part, right? Still missing these two fields here, which I bring outside as a derivative in j of x, right? These two came here, right? And all of that is applied to the integral of the exponential, which we know as z of j, and that's equal to 0. And that's another very important one, because again, and that's the main point here, if I now take, so this is the 1-point green function already, right here, right? And this one will have more derivatives in j, right? So again, I have an equation that involves 1-point green function, and who knows, many point green functions will come out of here. So again, this symmetry, just like happened in the case of the Schwinger-Dyson equations, right? These word identities also imply at the diagram level, right? Relations between diagrams or green functions with different number of external legs or green functions from different number of points, right? And these relations restrict what kind of diagrams a theory that has some global symmetry will have, right? So you will see that many times, especially when we get to heavy calculations, like trying to get renormalization and etc., that these word identities limit the shape, the most general form of the green functions you could have, because they have to satisfy relations that will come out of here, right? I can just now easily turn these just by doing derivatives in j and setting j to 0. I can get a huge number of equations that relate green functions, right? And we'll see that a similar logic will lead to what we call the Ward-Takahashi identities, right? Which are even more powerful, right? And but they come from local symmetries. In here, I just use global symmetry, right? But when you do that for global symmetries, for instance, you'll be able to prove, for instance, that the 1pi 2-point functions, right? Remember, pi 2 for the photon, mean u, right? It's the propagator of the photon has 2 indexes. So all the 2.1pi functions have 2 indexes, right? That this is 0 if you contract with the momentum, right? And that will imply some very specific form for this guy, and will guarantee that even at high loop order, nothing generates a mass for the photon. That's a consequence of the symmetry of the theory. So you see that these will be important, right? And they can be I use path integrals to prove them, but they can also be proven diagrammatically, order by order, right? You see Peskin does that in section 7.4, I think, right? So if you're curious, you can take a look there and how you show this one, right? Diagrammatically. Yeah? So that's all I had to say for today. See you next video.